Chapter 9 is all about exponential growth and exponential decay in different situations that deal with that. So Section 1 and Section 2 are very similar, so we're going to cover them at one time. Exponential growth is Section 1 and exponential decay is Section 2. Very, very similar, so we'll go ahead and talk about them at the same time. Your general formula for exponential growth is y equals a times b to the x, where a is your initial value, okay, or how much you start with, and b is your growth factor. Okay, so if we are growing exponentially, this number is always going to be bigger than 1. Okay, so if you want to go ahead and type in something into your calculator, so maybe we'll try y equals 2 times 2 to the x, okay, and take a look at that graph, you're going to notice that this is what your graph would look like. Okay, notice it is never going to go below the x-axis, okay, and it's going to cross, okay, right here at 2, okay, and it's always going to cross at your a value. It just happens to be in this case 2. So our intercept is always going to be at 0a, okay. As we look at that, as we go from left to right, our domain, okay, is going to be all reals, and then our range is going to be greater than 0, because again, that is never going to go below the x-axis. In fact, that's actually called an asymptote. If you remember from first semester, that's a line that the graph is never going to cross or touch. So our asymptote here is the x-axis. Okay, so that's what our graph looks like and some of the properties. Let's take a look at a story problem. Example A says in 1993, the population of the US was about 258 million. During the early 90s, the population was growing at a rate of 1% annually. Suppose the growth rate continues. Let P of X be the population in years after 1993. So if we are going to write our formula, we'll have P of X equals, okay, A is our starting value. Okay, remember our general formula is A times B to the X. So A is our starting amount. Okay, so we started with 258 million. Now I'm not going to write all the zeros out. I'm just going to label my answer in millions. Okay, and then I need my growth factor, which is 1%. So I'm going to take that and divide it by 100 and then add it to 1. So this is going to be the general formula for all of this. Okay, so what you're going to do is you divide your percent by 100 to turn it to a decimal and then add 1. So in this case, our growth factor is going to be 1.01. Okay, now maybe you don't need to do this step, okay, but remember, you're always adding because it's growing, okay, and then you always need to turn that percent to a decimal, okay, and then to the x. So there's my formula. So for part B, when will the population be in the year 2013? This is where your reading skills are going to come into handy. Okay, so 2013 is how many years after 1993, and that is 20. So you're going to let x equal 20. So you're just going to go ahead and plug that into your formula, 258 times 1.01 to the 20th. Be very sure here that when you do this in your calculator, you do the power first and then multiply by 258. And if you do that, you get about 314.81. And then remember to label in millions, okay? So unless you're going to put in all of the zeros, okay, which seems kind of ridiculous, you cannot forget the million as a label. Okay, part C then says, what will the population be in 1990? Well, that is before 1993 by 3 years, so we're going to have a negative exponent. So anytime you want to go back in time, you're going to make it a negative 3. So our formula here will be y equals 258 times 1.01 to the negative 3. Again, do your exponent first before you multiply, and you should get about 250.41 million people. Okay, and please do make sure that you are checking this on your calculator to get the same answers that I'm showing you here. Okay, sample B. Suppose an experiment begins with 300 bacteria and that the population doubles every 2 hours. Write the equation. Okay, so again, we're using the general formula, y equals a times b to the x, where a is your starting amount. So I'm starting with 300. Okay, and here's where it's going to get a little trickier. So b is my growth factor, right? Well, do you see a percent anywhere? I don't, but I see the word doubles. Okay, well, if something's doubling every time, that means I'm multiplying it by 2. So my growth factor here is 2. So we're not going to do it like example A where we divided it and added it to 1, because doubles is already bigger than 1 and it's just 2. Okay, so you only do that last process with the percent. okay? And then it doubles every 2 hours, okay? So I'm going to go ahead and say x divided by 2. Okay, if you just put x, you can't just plug in what they give you, so you need to take into account that it's every 2 hours. So we'll do that, so x over 2. Okay, so for part B, how many bacteria were there a half an hour after the experiment began? So now I can let x be a half of an hour, so I can let x be 0.5. So I'm going to say y equals 300 times 2 to the power of 0.5 divided by 2. It would probably do you well, okay, to do 0.5 divided by 2 first to get 1/4, okay, and then do 2 to the 1/4 power, okay, and then multiply that by 300, and you should get about 356.76 bacteria. Okay, probably even better just to say 356 bacteria, okay, because it's a bacteria. You're not going to have a portion of a bacteria. And then part C, how many bacteria were present an hour before? Okay, so now we're talking about a time of -1. Okay, so an hour before. So y equals 300 times 2 to the -1, and then the formula says divide by 2. Again, do your power first, and then multiply by 300, and you should get about 212 bacteria. Okay, the really nice thing about exponential growth and exponential decay is you can tell if you're doing things right. Okay, if I had 300, I should have a number less than that if I'm starting before the experiment. I should have a number more than that after, okay, because it's growing. So use those to kind of gauge if you're doing things right. Okay, exponential decay, section 2 is very similar. It's the exact same formula, okay, so it's the exact same variables. So A is still our starting amount, and B is still our growth factor. Okay, but by the name decay, you should be able to think that, oh, now it's going down, so now this number has to be less than 1. Okay, so that's the only change here. Again, if you were to go ahead and graph it, it's going to look very similar, only now our graph is coming down. So our domain is still all reals, our range is still greater than 0. It is still going to intercept at A, and the asymptote is still the x-axis. Okay, so same idea, just flipping it around. Okay, and this time our growth factor is less than 1. And the relationship to our exponential growth, if we were to graph these on the exact same, okay, the orange one is your exponential growth, you would see that these two are reflected over the y-axis. Okay, so they're a reflection of each other. So let's try some prehistoric problems. Example C, in 1998, a new Firebird Trans Am cost $15,798. Suppose the car depreciates, okay, that means going down 13% each year. So find the equation. Okay, so again, same equation, y equals a times b to the x. So y equals a is my starting amount, so 15,798. B is my growth factor. Okay, now here's where it gets a little trickier. So it's depreciating 13%. So again, I'm still going to divide that off by 100, but this time I'm going to do 1 minus that, okay, to get a percent of 87, okay, for my growth factor. So it's kind of an analogy for you be saying, if you got 13% wrong on the test, would I give you a 13%? No, I would give you an 87. Okay, so you're doing 100 minus what it's going down by. Okay, so make sure that is a really, really important key. Okay, so you're doing 100 minus the given percent to give you your B value. Okay, and then to the x, and x is always standing for time. So what is the car's worth in 2004? Okay, just read carefully. So 2004 would be 6 years after 1998. Okay, so we'll have y equals 15,798 times 0.87 to the 6th. Again, powers first. You should get $6,850.43. Okay, part C. What was the car's worth in 1995? Okay, so that's before 1998 by 3 years. So then for our x, that will be a -3. And then again, if we're going to gauge if we're doing things right, this car should be worth more than 15,798. So our value, when we plug this in, better be bigger than what we started with. Okay, and it is indeed. So $23,990.78 is what you get there. Okay. So example D is kind of getting into some science stuff. Carbon-14 has a half-life of 5,730 years. The original sample contains 250 grams. Write the equation. Okay, so same thing, starting value first. So 250. Okay, now I'm looking for a percent. I don't have a percent, but I have this nice thing called a half-life. Okay, a half-life, like it says, has a half for the growth factor, because that talks about how long it takes for that sample to decay by half. Okay, so 0.5 is always going to be true. Okay, for every time you see the word half-life. I don't really care about the fact that there's a 13 there. That's just a label on the carbon. Okay, and then my time is every 5,730 years. So x divided by 5,730 will be my formula. Okay, part B, how much will be left after 4 half-life periods? Okay, so if I want to know how much time that is in years, I would multiply the length of my half-life. So I would take that and say, okay, that needs to be 4 times 5,730, okay, to get the number of years. So I'll say y equals 250 times 0.5, that huge, so 4 times 5,730 over 5,730. Well, what do you notice here? Okay, the 5,730s cancel, so you're just left with the 4. Okay, and that's always going to be true because that exponent really is how many half-lives are going on. Okay, so now I'm going to do 0.5 to the 4th, times that by 250, and I'll get 31.25 grams. And I can't have a decimal here because I'm talking in grams. Okay, part C, how much will be left after 11,460 years? Okay, so years is what we're describing, so I'll just leave that. So 250 times 0.5 to the 11,460 divided by 5,730. Okay, you're going to divide that. Okay, you should divide it before you figure that out. So this is going to equal 2. Okay, now again, that's the number of half-lives. Okay, so it's just slightly different than B, but either way you're looking for the number of half-lives. So 0.5 to the second times 250 should give me 62.5 grams for my final answer. Okay, so the hardest part about these is reading your words carefully. Okay, so just read carefully. Part E gives us an equation, and we want to know the name of the graph. Okay, so I have a value, I have a b value, and I have to the x. And I notice that my b value is bigger than 1, so that makes this exponential growth. Part B says, what is the growth rate? Well, I know I added the 1, so that is really a 4%. Okay, so what you want to do is ignore the 1 because you added it, and then times that, okay, by 100, so take 0.04 times 100, give you a 4% growth rate. The domain for all of these was all reals, and 1 point on the graph. Well, I know the intercept always goes through A, so I know the 0.012 would be on my graph. Okay, so there's your first day of exponential growth and exponential decay. Take a moment and think, like this big rock stone thinking guy is telling you to do, and write down what you still have questions about and bring those to class tomorrow.